In this lecture, we're going to introduce the notion of a Galois group, which is the main object of study in this course. We begin with the definition. A field extension E of the field F is called a Galois extension if E is finite, normal, and separable over F. Consider such an extension. By the theorem on extensions of homomorphisms, we may view E as a subfield of the algebraic closure of F. Clearly, F may be embedded in its algebraic closure, and then, since E is a finite algebraic extension, then we can extend the embedding of F into F bar to embedding of E into F bar. By fixing such an embedding, we may consider that F is contained in E and E is contained in F bar. Let sigma be an arbitrary homomorphism of E into F bar. This is taken over F, meaning that sigma restricted to F is identity. Since E is normal over F, we know that this means that sigma of E is equal to E. So that is, sigma will preserve E as a set. And then this tells us that sigma is an automorphism of E over F. So this means that sigma is a map from E to E, which preserves field operations, and sigma restricted to F is identity. This motivates the following definition. The Galois group of the field extension is the following. So it's denoted Galois of E over F, and it's the set of all sigma from E to E. So these are automorphisms of fields such that sigma restricted to F is identity. And we point out that if this extension is a Galois extension, then this tells us that the order of the Galois group is equal to the degree of the extension. Since this extension is Galois, it is separable, and then the degree of the extension is equal to the number of embeddings of E into F bar. But each such embedding induces an automorphism of E and thus an element of the Galois group. And this gives us an equality that the order of the Galois group is equal to the degree of the extension. Next, we state the fundamental Galois Correspondence Theorem. Let E be a Galois extension of F. With the Galois group G, which is the Galois of E over F. 1. Consider the fixed point set E.g. So this is the set of X in E, such that for all sigma in G, sigma of X is equal to X. Then we claim that the fixed point set of E under the Galois group G is equal to the field F. 2. If we have an intermediate extension, so if K is a field between F and E, then the extension K to E is a Galois extension. 3. Let H be the Galois group of E over this intermediate field K. Then H is a subgroup in G, and the order of this subgroup is equal to the degree of the extension of E over K. And 4, there exists a bijective correspondence between subgroups H in G and intermediate subfields K that are between F and E. Under this correspondence, for each subgroup, we associate a subfield K, which is the fixed points of E with respect to this subgroup. And to each subfield K, we associate a subgroup H, which is the Galois group of E over K. So here, the first set is the set of all X in E, such that for all sigma in H, sigma of X is equal to X. And the second set is the set of sigma in G, such that for all X in K, sigma of X is equal to X. Let us prove part 1 of this theorem. Let alpha be an element of E which is fixed by all automorphisms from the Galois group. Consider field extension f of alpha. By homomorphism extension theorem, any map sigma of f of alpha into f bar extends to a homomorphism sigma hat of E into f bar. And since E is normal over f, we have that sigma hat sends E to E. So this means that sigma hat belongs to the Galois group of E over f. But alpha is fixed by all elements of the Galois group. So this tells us that sigma hat of alpha is equal to alpha. which means that there exists a unique embedding of f of alpha into f bar. So this tells us that the separable degree of f alpha over f is equal to 1. Since we know that the extension E is separable, this tells us that f of alpha is separable over f, since any intermediate extension of a separable extension is again separable. This implies that the usual degree of f of alpha over f is also equal to 1, which means that alpha belongs to f. And thus we conclude that the fixed point set of E with respect to Galois group G is equal to f. Let us now prove the second part of this theorem. So here, since we know that extension E is finite, certainly this implies that E is finite over K. And we also know that if we have a separable extension, then any intermediate extension is also separable. Now let us show that E is normal over K. Here we need to show that any polynomial f which is irreducible in K of x, which has a root alpha in E, factors into linear factors over E. To prove this, we consider G to be the minimal polynomial of alpha over f. Then the greatest common divisor of G and f is equal to f in K of x. This greatest common divisor is non-trivial because G and f share a common root, and f is irreducible in K of x. So this tells us that the only possibility for this greatest common divisor is to be equal to f. So this means that G is divisible by f. Since the extension E of f is normal, we conclude that G factors into linear factors over E. And then, since f is a divisor of G, the same holds for f. Now we prove that E is finite over K, is separable, and is normal. This tells us that E is a Galois extension of K. Now let us prove part 3. So what is the Galois group of E over K? So this is the set of sigma from E to E automorphisms such that sigma restricted to K is equal to identity. But the field F is contained inside K. So this means that if sigma restricted to K is equal to identity, then sigma restricted to F is also equal to identity, which means that sigma belongs to the Galois group of E over F. And we conclude that the Galois group of E over K is a subgroup in the Galois group of E over F. Now, the last fact we already pointed out, that if we have a Galois extension, and we know that the extension of E over K is Galois, then the order of the Galois group of E over K is equal to the degree of this extension. Let us now prove the last claim of this theorem. We need to show that this correspondence between subfields and subgroups is one-to-one. Let us denote the map from subgroups to subfields by alpha and the map from subfields to subgroups by beta. We want to show that alpha and beta are inverses to each other. Let us start with a subfield and apply our map beta and obtain a subgroup H, which is the Galois group of E over K. And then apply the map alpha and obtain the subfield, which is fixed points of E under H. But this is equal to K by our property 1. Our property 1 said that if we take a Galois group of an extension and then take fixed points under this Galois group, then we will recover our field. Only here we apply property 1 not to the field F, but to the field K. This tells us that the composition of alpha with beta is identity on the set of intermediate subfields. If we know that the composition of two maps is identity, then this tells us that the left factor is surjective and the right factor is injective. So here we want to record that alpha is surjective. Let us show that alpha is also injective. Let H1 and H2 be two subgroups in the Galois group of E over F, such that they have the same image under alpha. So that is the fixed points with respect to H1 and the fixed points with respect to H2 are both the same subfield K. Denote by the product H1, H2 the subgroup in G generated by H1 and H2 together. So this subgroup consists of iterated products of elements of H1 with H2. Since elements of both H1 and H2 will fix the subfield K, we conclude that K is fixed by this product H1, H2. But then the degree of the extension E over K is equal to both the order of a subgroup H1 and the order of a subgroup H1, H2. This tells us that these subgroups must be in fact equal, and thus H2 must be equal to H1. Now we proved that alpha is both surjective and injective, so this tells us that alpha is an invertible map, and beta is its right inverse, and the right inverse of an invertible map is the inverse. So this tells us that beta is the inverse of alpha. And then we have one-to-one correspondence between subgroups in G and intermediate subfields between F and E. This correspondence is given by the mutually inverse maps alpha and beta. Next, let us consider an example of such a Galois correspondence. Let F be the field of rational numbers, and let E be the splitting field of the polynomial x cubed minus 2. Since E is a splitting field, this extension is normal. And it is also separable because we are in characteristic 0. And obviously E is finite over F. So we conclude that E is a Galois extension of Q. The polynomial x cubed minus 2 has 3 roots. These are cube root of 2, then cube root of 2 times e to the 2 pi I over 3, and cube root of 2 times e to the 4 pi I over 3. So let's denote by zeta e to the 2 pi I over 3. So this is the third root of unity, so zeta cube is equal to 1. And then we see that the field E can be viewed as an extension of Q with elements cube root of 2 and zeta. Let us consider the chain of extension. Q is contained in Q with cube root of 2, and this is contained in E. Now, what are the degrees of this extension? The first extension has degree 3, because the polynomial x cubed minus 2 is irreducible. Now, on the second step, we join the element zeta. And what is the minimal polynomial of zeta over q? Well, zeta is a root of x cubed minus 1, but x cubed minus 1 is reducible because it has x minus 1 as a factor. So if we divide this by x minus 1, then we get x squared plus x plus 1. And this polynomial will be irreducible over q. And then we see that the degree of zeta over q is equal to 2. And by considering this tower of extensions, we conclude the degree of E over q is equal to 6. What can we say about G, the Galois group of E over q? The automorphisms in this group are determined by their images on the roots of the polynomial x cubed minus 2. And these automorphisms must permute these 3 roots. So each automorphism yields a permutation of this set of 3 elements, and we conclude that this Galois group is a subgroup inside S3, the group of permutations of 3 elements. But we also know that the order of the Galois group is equal to the degree of the extension, which is equal to 6. And since the group of permutation has order 6, this tells us that the Galois group contains all permutations in S3. Now let us label these roots as 1, 2, and 3, so that we can write permutations of these roots as standard permutations of 1, 2, 3. Now let us look at subgroups in S3. So for example, we have a subgroup of order 2, which is generated by the permutation 2, 3. So if we take this element 2, 3, then what does it do? Sigma sends cube root of 2 times zeta to cube root of 2 times zeta squared. Sigma sends cube root of 2 times zeta squared into cube root of 2 times zeta, and sigma sends cube root of 2 to itself. So in particular, so if we compare the first 2 equalities, then we see that sigma of zeta is equal to zeta squared. But what is zeta? Zeta is e to the 2 pi I over 3, or minus 1/2 plus root of 3i over 2. And zeta squared is minus 1/2 minus square root of 3i over 2. So this tells us that sigma may be interpreted as a complex conjugation. Restricted to the subfield E. It fixes cube root of 2, which is a real number, and conjugates zeta into zeta squared. So what is the corresponding subfield in E? The subfield which is fixed by the sigma or the complex conjugation is Q with a joint cube root of 2. Similarly, we can consider subgroups of order 2 generated by 1, 2 and generated by 1, 3. The subfield which is fixed by the permutation of the first two roots will be the third root. So it will be Q of cube root of 2 times zeta squared. And the subfield which is fixed by the transposition of the first and the third root will be a subfield generated by the second root. So it will be Q of cube root of 2 times zeta. We also have a subgroup in S3 generated by a 3 cycle, 1, 2, 3. Let us see how this subgroup acts. So if we take tau to be this 3 cycle, then tau sends cube root of 2 to cube root of 2 times zeta. Tau sends cube root of 2 times zeta into cube root of 2 times zeta squared, and tau sends cube root of 2 times zeta squared into cube root of 2. If we divide the second equality by the first, then we will see that tau of zeta is equal to zeta. This tells us that the fixed subfield to the subgroup is Q extended with zeta. Finally, we have two trivial subgroups in G. So we have G itself and we have the identity subgroup. The first part of our theorem said that the fixed point subgroup that corresponds to the whole Galois group is the field F, which is Q in this example. And by definition, the set of elements that are fixed by identity element is the whole field E. And since from group theory we know that this is a complete list of subgroups inside S3, by the Galois Correspondence Theorem we obtain that this is a complete list of subfields inside the field E. What we see in this correspondence that the bigger subgroups correspond to the smaller subfields. So for example, if we take the Galois group itself, then it corresponds to the smallest subfield, which is the field F. And if we take the smallest subgroup, which is the identity subgroup, then the largest field will correspond to the smallest subgroup. Let us state this observation as a formal result. Corollary. Let ki's be subfields between F and E, and hi be the corresponding Galois groups. And I here is 1 or 2. Then K1 is contained inside K2 if and only if H2 is contained inside H1. So we have inverse embedding relationship between subfields and subgroups. Let's consider the proof. And let's look at the forward direction. So suppose K1 sits inside K2. And let sigma belongs to H2, so which is the Galois of E over K2. Then sigma restricted to K2 is equal to identity. But K1 is a subfield inside K2, so this tells us that sigma restricted to K1 is also equal to identity. And then this means that sigma belongs to H1, to the Galois group of E over K1. And hence, we conclude that every element of H2 sits inside H1, so H2 is a subgroup inside H1. Now let us prove the backwards direction. Suppose H2 is a subgroup inside H1. By Galois correspondence, the subfield Ki is the fixed point of E with respect to Hi. Let X belongs to K1. Then, for all sigma in H1, we have sigma of X is equal to X. But H2 is a subgroup in H1, so this tells us that for all sigma in H2, we have sigma of X is equal to X. But then this tells us that X belongs to the fixed point set in E under the action of H2, which is equal to the subfield K2. So if X belongs to K1, we concluded that X belongs to K2. So this means that K1 is a subfield inside K2. And this completes the proof of this corollary.